Okay, so let's continue. Last time we defined self-energy bubble, and we mentioned that we could ignore the crossing diagrams and only sum over all this bubble or ring diagrams, and then we can form infinite number of terms in this summation, which we will summarize it as the Dyson's equation, which is very well known, equation for self-energy. So today we will continue and deriving such a Dyson equation for self-energy. So diagrammatically you could consider this so-called full self-energy, which is the bubble with this two different lines that are kind of intersect with each other. So this is called full self-energy, which includes infinite number of this sigma star, which we call this one particle irreducible self-energy diagrams. And you can see very clearly that we could have one bubble made of the sigma star, or two bubbles, and three bubbles is any number of bubbles, and the single bubble, which is the shaded with one particular orientation, which we call this sigma star, and which is so-called the proper self-energy. So the proper self-energy is this basic unit of self-energy diagrams up to the first non-trivial order. In this case, it is up to this first order in potential, right? Which is first order in potential. And in particular, this means that we sum over these two diagrams. Okay, so a single balloon and this kind of a loop diagram made of the solid line and wavy line. So we could simply just repeat these diagrams by connecting all the single bubble, and we can make it diagrams with many, many bubbles. And you can imagine that we can sum over all such diagrams and we get some approximated form for self-energy. Of course, this is not the full story because there are many other diagrams that are very complicated and they are crossing, so we neglect all these complicated messy diagrams and we only sum over these ring diagrams. But even so, this sigma full can actually tell us much about the self-energy of the system. Okay, and this is the definition of a proper self-energy, where there's no single line here connecting these two bubbles. For example, this, and this is one particle irreducible diagram, which means that if we cut one line, it does not fall into two disconnected pieces. Okay, so like this is not the irreducible diagram because this is reducible. We could reduce this diagram by cutting through this diagram into two pieces, and each piece is actually irreducible diagram. So we connect all these irreducible diagrams and they become reducible diagrams. And we sum of all possible reducible diagrams made of irreducible self-energy. Okay? And then we could formally just write it down, all these expressions, by summing over all this diagram, like this. The first term is the bare propagator, or the bare Green's function, right? And the second term is actually this first non-trivial order to include the self-energy. This one irreducible self-energy diagram, which is precisely this stuff right there. You can see that this G013 is this propagator, sigma star is this bubble in the middle, and the right propagator is G042. Okay, so likewise I could translate this two bubble diagrams like this: external leg and a bubble, and another external leg and another bubble and external leg. Of course, we need to sum over all internal degrees of freedom. In such case, this is R3 and R4, and the third term is the integral over three internal variables, four internal variables, D3, D4, and D5, D6. Now this labeling, this 3, 4, 5, 6 are simply just the coordinates of this internal degrees of freedom. Okay, so you can imagine that I could just keep expanding this self-energy diagrams by connecting more and more one-particle irreducible diagrams, and I could just reorganize these terms in the following way. So the first is G0 plus the integral over G0 times sigma, and I can actually combine all these different bubble diagrams, and you can see very clearly that there's a common factor G0 sigma star that I pull in front, but inside the bracket is actually again G0 plus G0 sigma star, G0 plus blah blah blah, and therefore the whole thing inside the bracket itself is what? The G4, right? Okay, so then I could simply just rewrite this expression in terms of the G4 inside this integral and multiply by sigma star and G0 and plus this Bayer propagator. Okay, so you can see very clearly that on the left-hand side of this Dyson equation, it is a G4. On the right-hand side of the integral equation, there's also a G4, right? So, but we know that G4 is something that we need to solve. But this appears on both sides of the equation. As a result, we need to solve this equation self-consistently and iteratively. And this is what we call the Dyson equation, okay? Which means that in order to get this G4, we need to plug in this zeroth order approximated form of G4 right on the right-hand side of the equation. We integrate over the whole thing, right? And then we consider this as the first order result for the G4, and then we plug in the first order result again on the right-hand side of the integral, and then we get the second order approximation for G4, and so on and so forth until we get the convergence, meaning when the G4 that we plug in here is what this is the nth order result, which is given by G0 plus the integral G0 sigma star and G4, but up to n minus 1 iteration. So, and you will get the convergence if the nth order result is almost the same as the previous result. Okay, so we get convergence if Gn is roughly almost the same as Gn minus 1. Okay, and the capital N refers to the nth order iteration. So you need to iterate this integral equation up to nth iteration and steps. And suppose that this nth step, we get this G4, and we know this the result from the previous step, Gn minus 1, if they are really close to each other. Okay, so we can say that this result is actually convergent, so that we stop the iteration. So we find the solution. And if not, then we should keep iterating this integral equation until we satisfy this convergence. Because of course, you could set a particular goal for this convergence. For example, if you could actually get arrow bar like this, which I call this delta G, okay, at any given omega or k, and you could actually subtract this 2 at different neighboring iteration. So if this delta G is actually very, very, very small, so you can actually define how small is your tolerance. Okay, so if this satisfies your tolerance of this arrow bar between n's and n minus 1 iteration, and then you get a convergence. Okay, so oftentimes there is no analytical solution for this Dyson equation, so we need to do this numerically, but it can be done. Okay, and this is a very practical and useful equation to get the self-energy correction of the Green's function. So once we found this self-energy sigma full, then we could actually plug in back to the Green's function, we get this full Green's function. So this is the next job.
Yeah. When we talk about the progressive energy, you cannot become too disconnected. But for the bubble and ring, it's separatable, right?
Right. So these are reducible diagram. Okay, but basic unit is this sigma star, which is irreducible.
But in fact, this is still can separate by two parts, right?
Oh.
By one.
Like this?
No, bubble and the ring separate.
You draw it right here.
I just, oh, sorry. I mean, I see, can I do it?
No. These are two separate diagrams.
Oh, okay, I see. Okay.
They're just two separate contributions. Okay, of course they're separate. Okay, what I mean by this proper self-energy is that for any one of this diagram, you cannot make this diagram a completely independent diagram like this. Any other questions? No? Good. So let's just take the Fourier transform, and we could formally derive these four Green's functions based on this Dyson equation. So G4 in K omega space is given by G0 K omega n plus G0 K omega n times sigma star K omega n times G K omega n. All right, so I simply just remove all this space and time integration, D3, D4, and so on, by taking the Fourier transformation from the real space time to the Fourier space, okay, in the K and omega space, so that there is no integral anymore. Okay, so I simply just get rid of all this time and space integration, and this is the Fourier representation of this G4, and this is what we want to know, right? Okay, the G4 in K and omega space, which is given by this bare propagator G0 and all these self-energy corrections, right? But of course, on the right-hand side of this equation, the second term, there's again a G4. However, if you look at this expression, this G4 K omega, isn't that the same appearing on the left-hand side? Indeed, they are the same. All right? So that's the trick. Okay? But if you look at this Dyson equation in real space and you don't recognize this because this is G1, 2, but this G4, 2. And G4, 2 is actually hidden inside this integrals. You don't know that they're in the Fourier space, they are identical. Because you cannot simply just move this around because this is to be integrated over real space representation. So that's the reason why we need to take the Fourier transform. And you can recognize that these two G4 are exactly the same. So now you could just rearrange this term and by taking the inverse of the GK omega, which is G0 inverse K omega minus sigma star K omega n. Okay, so can you derive this? Really simple. You simply just rearrange this to G4 on both sides of the equation and take the inverse of this, you get this simple Dyson equation, and you invert that, you get the full Green's function. 0 inverse minus sigma star. Isn't that simple? Because this is what we need to know. Okay, suppose there's no self-energy correction, so suppose this free system, there's no interaction between any particles, so you get only G0. And suppose this is 0, and the 1 over G0 inverse is precisely G0, okay? And if interaction vanishes, then G is the same as 1 over G0 inverse, which is G0. Okay, but if V is non-zero, then we should really first compute the sigma start, and then we'll plug in here in the denominator, and then we add this G0 or subtract from this G0 inverse, and then we invert the whole thing, and we get the full Green's function. Okay, and so this is a way that we can actually solve for this G4 as a function of k omega n. So of course this is in this Matsubara frequency domain. So we need to make analytic continuation going from, say, above or below this imaginary axis. Remember that omega n goes to omega plus or minus I eta. Remember that. And what is omega is the real frequency. Okay? So it corresponds to this real AC field or AC frequency or external energy frequency that you inject in the system. So then this really corresponds to this measurable quantity, which we call this G capital. Okay, and then this corresponds to all these physical observables that you can measure in the lab, right? By taking the real imaginary part of the G capital and as function of k and omega, and then you know everything. Okay, so this is a good way to make progress, and it's the simplest possible way to make progress. Good. So we will take a very simple example later based on this Dyson equation for G4, and then we can actually get useful information out of this. Okay, so let's take a short break. So we are almost get to the end of the Green's function and to actually get to the beginning of this examples in the real physical systems, such as the Anderson localization problem or Coulomb interacting electron gas and electron phonon interactions and the BCS theory of superconductivity. So all the examples that I just mentioned could be studied, and we can make progress by using this Dyson equation. And you will see that this is extremely useful and powerful method that allows us to study the Green's function of this interacting system, and then to extract this real imaginary part of this correlation function. And later we will make connections between this G4 and all these measurable quantities, such as dielectric functions of metals and insulators, and also this charge transport, electron transport in Anderson localization problem.
Professor, I have a question.
Yeah.
Because you use this trick to do a kind of infinite sum, right?
Yes.
And just take a probability of energy, do the infinite sum. But according to experiments, after this answer, if we add the second order Feynman diagram, it will have a big contribution.
Are you saying that sigma star, if we simply just use this lowest order?
Correction.
I say, 如果全部都已经有个 sigma star， 然后但是我已经丢掉第二阶的其他的项目，对吧？那如果把那些加回去，那会不会有重大的风险？
What's your question? So this is my sigma star, right? Which is just up to the first order in interaction.
Yes, and you use this to the infinite sum.
That's right. That's
yes.
right.
And
What's your question?
Yeah, my question, but we ignore others second order. I mean, two wavelength line, right? We ignore others. We just pick up this kind of infinite sum.
Of course, you could imagine that I have other second order diagram where you have. So let me just go back to my earlier notes and to illustrate this point. Yeah, good point. Of course, this is just up to first order in V as this estimation of sigma star, but of course you could imagine that I have some energy like this, right? Okay, this will be a second order contributions to sigma in this potential, in order of V squared, right? This is your question. So what if I include this to the sigma star, and how is this going to change the result, right? Okay, of course, the answer depends on the nature of your interaction. Okay, so if this V is just a weak perturbation, okay, suppose this is not the strongly interacting system, okay, which we show, of course, in the later examples Of course, there are some systems that the second order corrections to these interactions contribute to the sigma star will make a difference, but in many other systems it will not make any difference. Of course, you could add this diagram to your sigma star, and the best way to check whether they have any difference is you simply just go ahead and include this and see what happens. Okay, so you could simply just compare this diagram, the results coming from this second order diagram, with the first order diagram right there, and see which one dominates. Okay, if you find the second order dominates over the first one, then you are in trouble, because this kind of a perturbed expansion is not justified. Okay, so we have to make sure that the high order terms should be much smaller than this lower order terms. Otherwise, this cannot be justified as a perturbed expansion. Of course, it will make some difference, but in many cases, this difference is tiny, so we can safely neglect this. You can imagine that if this is true, then why not including third order, fourth order, infinite order? Of course, if you really want to do this, well, you should do that. Okay, but practically speaking, this is not possible to actually exhaust all this nth order diagrams to sigma star, in particular for those systems that can be perturbedly studied, and those second order term in sigma star can be safely neglected. That's for sure. So we will see some examples later. Okay, so you can compare your results with the experimental data and justify whether you are able to do so. Yeah. And in the meantime, we already ignored all this crossing diagram, as I mentioned, right? So this kind of diagram are not included. You may wonder, how important are they? Of course, in some cases they are important, but in many other cases they are not important. Okay, so of course, as I mentioned previously, that this is not exact solution for the Green's functions. You mentioned we ignored many diagrams. Okay, maybe some diagrams that we already ignored are important. We didn't know. Okay, but well, of course, when you notice that this makes a huge difference, then you should consider or reconsider the method that you are using. Okay, maybe this kind of a perturbed expansion is not good, because the higher order terms contribute even more, right? Okay, but practically speaking, this is good enough. This is good enough. So that's my answer. But of course, this is not exact, okay, but it's reasonably good. So this is kind of a trade-off, a compromise. You know that you don't have the full solutions analytically, but you need to do something, right? You need to make progress, but how can you do this? Of course, we need to throw away some unimportant terms, but whether these unimportant terms are really unimportant is the issue. We need to justify, of course. And so one way to justify this kind of approximation is to estimate the higher order contribution to sigma star, as you mentioned. If they are really tiny compared to this first order term, and you could just forget about this. But if they do contribute much, then you should rethink about whether this kind of approach works, because we cannot accept that this higher order term are more important than the lower order terms. Okay, so great. So let's continue. So as I mentioned, we could get the capital GK omega by analytic continuation. So let's do it. Of italic G to capital G. As I mentioned previously, when we studied this analytical properties of the Green's function, so we mentioned that both G retarded and G advanced Green's function in real frequency can be obtained by these analytic continuations from this G italic, either from above or from below. If we perform such an analytic continuation from above, then we get G advanced, and from below we get G retarded. Okay, so let's just realize this in this very simple, naive, non-interacting fermion or electrons. So we know that G capital 0, when we do such an analytic continuation, so we identify this I omega n, I times I omega n as real frequency plus I eta or minus I eta. So you check your notes. Right. So it's given by this expression. Perhaps this is minus, this is plus. Okay? And later, we will include the self-energy in this expression when we perform such an analytic continuation. And let me just write down this G4. Suppose we fix at 0 temperature. And G0 plus I eta sine omega minus mu. Remember, when we do this analytic continuation from this imaginary axis to real axis, real frequency, and we have such a pole structure, right? So the pole for this omega below chemical potential Fermi energy are all slightly above this real axis. And for this omega larger than mu, the poles are slightly below the real axis. Okay? As a result, you need to add this small imaginary part plus I eta times the sine function. So the sine function reports out to you a plus 1 or minus 1, depending on whether omega minus mu is positive or negative. For positive, sine is positive. For negative, the sine function gives you negative. Okay? So, and this is what we need to do. So we need to calculate the sigma star and plug in here, and then we get all we want to know. In particular, this sigma star oftentimes contains the real imaginary part. So the sigma star as function of Ken omega is not just a real function of Ken omega, it's a complex function of Ken omega. So it carries both the real and imaginary part. And it is this imaginary part of sigma star which gives you this quasi-particle decay. The quasi-particle decay with a rate which is proportional to the imaginary part of sigma star, which we call this gamma. So if you calculate this, say, some kind of a correlation function, there will be an exponential decay, gamma t, like this, which means that this correlation between any single particle or single electron over time is actually exponentially decayed. Okay? And the decay rate is given by gamma, and gamma is proportional to the imaginary part of the sigma star. Okay? In other words, if we have this imaginary part of the sigma star, then this quasi-particle do not live forever, so they must decay over time. They must interact with the other particles by this interaction, so the interaction actually make this quasi-particle unstable, and they can actually decay into other particles by this interaction. Okay, so we will see this when we talk about specific examples, such as this Anderson localization problem. So let us just start to do some math, okay? Because, as I mentioned, the sigma star, this is sum over these two irreducible diagram, right? So we need to evaluate this Matsubara sum. So typically, the sigma star contains integration over internal degrees of freedom, and which involves this Matsubara sum and also this moment integration. For the specific example that we just showed, sigma 1 star, which is this bubble plus this loop, and it is given by this, right? So we already derived such an expression, this Fourier transform sigma 1 star, and there are two things that we need to do. First is to perform this Matsubara sum over omega n prime, and the second is to integrate over k prime. But this is something that we need to do first. It's called frequency sum. So we need to apply the knowledge that we learned from this applied math or mathematical physics, that we can perform the contour integration when we sum over this Matsubarra frequency. So let's try to perform such a Matsubarra sum. Suppose we have such a factor, sum over n e to the I omega n eta divided by I omega n minus x, where this x is defined as epsilon 0 k prime minus mu, for example. So this is something that we need to sum over. And we have two types of Matsubarra frequencies, one for bosons, another for fermions. So boson carry even integer multiple 2 pi divided by beta, and fermions carry odd integer multiple of pi divided by beta. So we will see next that we could generalize this Matsubarra sum to the complex plane. So let's suppose this I omega n, which appears in the vertical pure imaginary axis, which could be generalized to complex variable z, and this x is taken to be some real valued stuff, which is in this case epsilon 0 k minus mu. Next, we will try to perform such a summation over Matsubarra frequencies by considering the contour integration. So most direct approach to perform such a Matsubarra sum is to use the contour integration. And we could generalize this Matsubarra sum to the complex contour integration, and we know that there will be a pose right along the imaginary axis, and we will also see that we have some pole right at the real axis when z equals to x. So we will extend this contour by extending this kind of a vertical imaginary axis to both sides of the complex plane, and we could actually convert such a Matsubarra sum to the contour integrations on both sides of this vertical axis, and which we will see in just a moment. In other words, we will show that instead of summing over this vertical axis imaginary frequency, and we should go the contour following this yellow line C, where the C will actually extend to both sides of this imaginary axis. So let's take a short break. When we come back, we will start to deform this contour. So for this, you could check either Feta-Velachka or Flansburg. So there are detailed explanations of this contour integration. So let's start this contour integration. As I mentioned, what we need is to perform such a Matsubarra sum, and there's a prefactor 1 over beta in front of this Matsubarra sum right there, and the denominator will get e to the I omega n eta, in the denominator will get I omega n prime minus this epsilon 0 k prime minus mu. So let's just try this. Let's consider this contour integration, and later we'll see that this A, this red A, capital A here, which involves this beta over 2 pi I times this contour integration, this is exactly what we need. So let's do it. Suppose we generalize this formula to this complex contour integration like this, and I will integrate over this contour, and we will see in just a moment that this is precisely what. And we separate this Matsubarra sum into two cases. One is for boson, another for fermions, and we'll just calculate both bosonic case first, and then we will demonstrate that for fermionic case we'll also get the same result. So let's just try to perform such a contour integration. And so let me just make a contour plot like this. So previously, we only consider the imaginary frequency, Matsubarra frequencies, which are along this vertical lines here, where this two-dimensional plane represents the complex variable z. And all these crosses represent this pole of this contour integration right here. So you could see very clearly that there are a bunch of poles happening with this factor, 1 over e to the beta z minus 1, and this occurs when this e to the beta z equals to 1. So when that happens, which means that the z is actually 2 pi I times n divided by beta. When that happens, you get a simple pole because of this factor. And this is precisely this even Matsubarra frequencies or bosonic Matsubarra frequencies, and this factor, beta divided by e to the beta z minus 1, has poles right at that this Matsubarra frequencies for bosons, with a unit residue. So if you apply the residue theorem for this factor, and you'll get a unit residue, which means that you get 1, because there's a 2 pi I in the denominator. So this residue, if you apply the residue theorem, you'll get exactly 2 pi I divided by beta, so you get cancellations, and you get just residue being 1. Okay, so you can see very clearly that you get a bunch of these poles right at the vertical axis right here, with an even Mossbauer frequency. And then you have the residue. So if you combine these two factors, including this convergence factor and 1 over z minus x, altogether this residue, the whole residue is given by this 1 over beta times this factor. So if you simply just plug in the z, when you get vanishing of the denominator of this term, and z is actually I omega n. And e to the eta z becomes e to the I omega n eta. So if you collect everything, so this is precisely what we need. Remember, previously we need this stuff, this summation. In other words, if we take this contour integration like this, and there is a pole in the real axis when z is actually x right there. But previously, when we sum over this Mossbauer frequencies, we only consider the imaginary frequency, vertical axis. But now, since we try to extend this Mossbauer frequency sum by this complex contour integration, so the contour that I mentioned is actually along the C. Right? So this is contour C. So if you enclose this contour, this red contour, and you'll find that this complex contour integration reproduces what we need. Okay, this Mossbauer sum, because it encloses all these simple poles along the vertical axis with this even Mossbauer frequency. But now we could actually deform such a contour from this red circle to this kind of shape, the orange contour. So let's just try to deform such a contour. And we will see in just a moment that this kind of a deformed contour is precisely what we need. Remember, previously, on the right-hand side of this plot, we get this red circle. This red circle is right here, this one. So let me just use yellow. So we will see in just a moment that all these integrations outside of this red circle don't contribute to this integral except this pole right at this z equals x. So the argument is this: we could extend and distort the contour from this red circle, which is this one. And remember, when we deform this contour from the red circle to this orange contour, we actually make such an approximation that very high values in this I omega n along this imaginary axis and well below this real axis, or almost plus or minus infinity, above and below this real part of z is actually negligible. So we actually use a dash or dotted line to actually represent such part of the contour. So you could actually connect this and that, but you could also neglect this part, the small part of this contour marked by a white arrow above and below, for the reason that I will describe later. And then this oval shape of this red contour now becomes just two vertical lines on the left and right of this vertical imaginary axis. Okay, but this contour could be further deformed or distorted into this butterfly shape. So this is like this, and you connect this part. Okay, so you could simply just stretch this contour, and you know that they are identical. So let me just plot it right here. So suppose I have these two vertical lines right there, and I can simply just deform by the complex analysis that these two vertical lines could be further deformed, distorted in whatever shape I like, right? So if you stretch this two curve, you get two vertical lines. Imagine these two are just two strings, and you could deform this string to any shape you like, and this is particular shape I like, because this shape, we can pick up the pole right here when z equals to x. So these two contour integrations are identical, provided that this part of integration are negligible, and we can justify this approximation from this convergence factors, eta z, where z goes to plus I infinity or minus I infinity. Okay, but instead of focusing on this part of a contour integration enclosed by red, and we should focus on this integration marked by orange line right there. Okay, but if we can show that following this orange curve, and we get a residue contribute from this z equals to x on this real axis, but all the other contributions are zero, almost zero, because of the convergence factor, then we are done. So let's just try to make such a identification or such a equivalent expression. So we know that this is exact, right? Because if we focus on this vertical axis, and this is precisely what I just shown you on the left-hand side of the blackboard, but instead of enclosing this pole along the vertical imaginary axis, we should do it a different way, because that's can actually give us to this very simple result, okay, which is following the orange curve. So this is what we should do. Okay, so and let's just try to do it. So along this orange contour, we have different parts, so which are marked by the contour C prime on the right and contour C prime on the left, right? And also this gamma above and below the real axis. Okay, so we will see in just a moment that only the integration near this real pole at the real axis z equals to x that will contribute to this integration, and all the other parts of the integration are negligible because of this convergence factor e to the eta z. So let's take a short break. When we come back, we will analyze this calculation in more details. So let's try to deform this contour from the yellow circle to actually orange curve or orange contour, which is made of C prime on both sides of the contour, and also the gamma contour on top and the bottom of this path. So, and let's just try to evaluate this integrand on all these different parts of this contour. Okay, so first on this contour gamma, which appears above or below the real axis, and there this magnitude of z goes to infinity because this place is really far away from the origin, right? So this is really far away. So any part of this gamma contour, the magnitude of z goes to infinity because this is very far away from the origin. And also this, suppose we just consider top contour appearing on the positive side of the, say, the real z. So suppose the real part of z is positive and the magnitude of the z goes to infinity, and so the integral is proportional to 1 over the magnitude e to the minus beta minus eta times the real part of z, which goes 0 when the z magnitude goes to infinity, and at the same time beta is much larger than eta. Remember, eta is a really, really small positive number, right? So beta is 1 over kBt, which is always positive. And at any finite temperature, this 1 over kBt is much larger than this eta. Okay, so beta minus eta is always positive, and this real part of z is positive by our assumption, and there's a minus sign right there. So when z, real part of z is actually also approaching infinity, so there's this 1 over infinity times e to the minus some positive number times almost infinity. Right? So it's e to the minus infinity divided by infinity, okay, which is negligible. As I mentioned, this is the power of a convergence factor. Suppose we do not include such a conversion factor, then we're in trouble, because we cannot simply just make them go away because they will contribute to this contour integration. However, if we put this conversion factor correctly, then we can safely neglect all this part of the contour integration. We can only focus on the poles along the real axis. Good. So therefore, the integral along the gamma vanishes. So in the same way, we could also show that for this gamma contour below this real axis, and also get this vanishing of this contour for this gamma. Good. So as a result, this original Matsubarra sum now becomes the contour integration over only C prime, right? Because all these gamma contour integrations are gone, so you end up with only this part, the C prime part of the contour integration. So, and you know very well that this along this left side of the C prime, there's no pole, no divergence. And so these two integrations from the left to the right cancels out by the other parts below the real axis from the right to the left. So these two parts of the integration got exactly canceled. And so we left with only this part of the integral. Okay, so the only singularities occurs when z equals to x. So by Cauchy's theorem, so you know very well that you simply just go around this contour along the C prime, and then you pick up the pole, the residue right at the pole, and this is the final result. So let me just write it here. So by Cauchy's theorem, it's given by this. Notice there's a minus sign right there. So you simply just replace z by x and plug in here and calculate the residue. And the residue is given by 1 over e to the beta x minus 1 and times beta and overall prefactor minus 1. This minus 1 comes from the fact that you simply just go around this pole, say clockwise, right? Along the C prime contour, you actually go around the pole clockwise. And by standard definition of a complex analysis, this gives you extra minus 1. So because by definition, by convention, this residue gives you plus 1 if the contour is actually going around this pole counterclockwise. So for the clockwise contour, there's extra minus sign. So this is the reason why you get the extra minus sign. So now you can see the power of this convergence factor, right? So it could actually further simplify this Matsubarra sum, and this Matsubarra sum reduces to simply just evaluating the pole, the residue, right at the real axis. So now we learn a lesson. So this Matsubarra sum for the bosons, including this convergence factor, give us this very simple result where you have this beta over this e to the beta x minus 1 in the denominator and overall minus sign. So now let's look at this fermion case, when the Matsubarra frequencies are fermionic, meaning this is 2n plus 1 pi divided by beta. So I leave this to you as a homework exercise. C eta and beta divided by e to the beta x plus 1 with a plus 1 prefactor. So this is the homework. Derive it. So you can follow the same strategy that we did for the bosonic case. And the fermionic case, you could still get the same result. Okay, except now you get the plus 1 in the denominator between 1 and the e to the beta x. And also the overall sign is plus 1 rather than minus 1. So we make further progress because now we can actually plug in this result back to this momentum integration. Remember, the self-energy evaluation needs two types of summation. One is the momentum summation, another is Matsubarra sum, and we just finished this Matsubarra sum. So we plug in this factor for the boson fermion case back to the self-energy, and we will see what we get after the short break. So nothing is difficult because you learn complex analysis, and this is the place that we actually take advantage of this complex contour integration. So let's just finish the job. So we plug in what we just did when we sum over mass and power frequencies, and this is the final result, okay, for sigma 1 at first order self-energy corrections. And there are two terms, remember. The first one is when momentum transfer is 0, you get a single balloon. And the second one is we have a finite momentum transfer, V as function of k minus k prime. And then we have this thermal factor right here in the denominator, so which is given by simply just a Fermi-Dirac or Bose-Einstein distribution. Okay, so when we further integrate over this k prime, and we get the full description of the sigma 1 k. Remember, the simple example, you don't have the frequency dependence of sigma 1, but in more complicated cases, we do have both momentum and frequency dependence for the sigma 1. Okay, so I guess that's the end of this introduction to this Green's function and this Dyson equation and stuff. So in the following, we will introduce specific systems, for example, the Anderson impurity problem or Anderson localization problem, and also Coulomb interacting electron gas, and electron phonon coupling, and the BCS theory. So all these 4 different cases are really familiar to you because these are the topics of the elementary solid state physics, but we didn't know about this technique, the Green's function technique. And so since we have this powerful tool to compute this self-energy, so we can simply just use this Dyson equation, and we could actually get something that you didn't understand in the introduction level of the solid state. In particular, the quantity that depends on momentum and frequency when you take the measurement. For example, this dielectric function, okay, is function of a momentum and frequency. This is called this AC dielectric function. So this stuff can be measured, but it's really challenging to actually compute this theoretically without the knowledge of Green's function. But now it's time to compute this physical observable as function of k and omega when we include the self-energy correction. And another example, such as this electron scattering rate, 1 over tau, where tau is the mean free time. So you could also consider the scattering time or relaxation time as function of k and omega, and also temperature. But this kind of a relaxation rate is impossible to be computed if you don't know this Green's function technique. But this kind of a relaxation rate could be estimated by the semi-classical Boltzmann type of integral, right? But this is only semi-classical. A full quantum mechanical treatment is absent. Okay, so you know the experimental facts, phenomenology, you know the semi-classical, but you don't know the pure quantum mechanical treatment for this 1 over tau. So there are millions of examples that you could see in the solid state textbook that required the knowledge of the Green's function technique. So that's what I emphasized many times at the beginning of the course, that the Green's function is everything. So everything you need to know is Green's function. Okay, so let's just start the simplest example that you can imagine, but this is not simple at all when it was first studied by Anderson, which is electron scattering by impurities. So let me just define this system. Suppose I have a piece of metal. You know very well that in solid state we have periodic arrays of these atoms, and there's some many electrons go around this ion cores like this, and these electrons can hop around between neighboring sites. So if we have a half-filled electron band for the piece of metal, and these electrons can actually conduct. However, if you imagine that I remove part of this atom or ions from this lattice, then I create an impurity, meaning I create a hole right here, and I could put it any way I like. I could actually randomly just remove part of the ions from the lattice, and I can create many randomly distributed impurities. So when we have such a randomly distributed holes or impurities, effectively you create very strong delta function-like potential that we discussed previously, that you actually create some very strong, say, repulsive potential, because now the site is empty. So you actually forbid all these particles actually close to that empty site. And we will study this randomly distributed, say, empty sites or impurities embedded in this piece of metal. And you can see clearly that the electrons can actually get scattered by another electrons, but very close to the impurity, electron will experience very strong repulsive interactions like this. So electron actually come in, but then it gets deflected away by this delta potential. And we could try to construct a model, a very simple model, which is the delta function like this impurity potential, which actually interact with a single electron. So that's the simplest possible model Hamiltonian you can imagine. But on top of that, you will consider this randomness in the system by considering a randomly distributed such impurities. And Anderson studied this long time ago, and he concluded that for one-dimensional metal wire, if you have such just one or two or very few randomly distributed impurities, and this will destroy everything. So this metal wire becomes insulator right away. This is called Anderson localization. For a one-dimensional piece of metal, if you randomly remove some atoms and which creates such a delta-like potential, then this dramatically changes the electrical properties of this metal wire. So this metal becomes insulator. And this phenomena was confirmed, say, in the 1960s, and even there are many examples showing this Anderson localization phenomenology, where you just take almost one-dimensional wire, a metal wire, and then you use some experimental trick to introduce some kind of a random potential. And in such case, this system loses metallic behavior and the resistivity actually goes up as you lower temperature. But why is that? So we have now the theoretical understanding of this Anderson localization phenomena if we actually analyze this problem by using this self-energy correction and this kind of a vortex correction and so on. So we will introduce another correction diagrammatically which go beyond this self-energy, which we call this vortex correction. But first, we have a good understanding of this kind of electron scattering by impurities at the level of the scattering time, or this relaxation rate. You need to show that these two procedures are identical. I'm not sure this is identical procedure. So these kind of impurities must be random. But the impurity concentration could be as low as possible. If you simply just remove some, just a couple of atoms away, but you do it randomly, then you find that this is Anderson localization. But if you have just one site removed, then I'm not sure this will give you anything different. So the disorder and randomness are also very important when we talk about Anderson localization problem, because we need to perform so-called impurity average or disorder average. So we will get there pretty soon. So let me just define this model. This is the simplest model. So we have a perfect host atoms, which is the uniform charge neutral background, and all the impurities are the same. So they are located at the position capital RL randomly. So this is RL. And the number of impurities are Ni, capital Ni, in a volume, omega. So you get impurity concentration, little ni, which is capital Ni divided by this volume, omega. So the job is to compute this electrical conductivity, which we call the sigma, for a given configuration of this random impurity. So we need to take this disorder average of this sigma over this disordered impurity configurations, which is given by integrations of all possible impurity configurations with a probability. Okay, so f as a function of this impurity position, capital Ri, represents the probability of finding such a, say, impurity configuration. Suppose this is one possible way to think about this impurity, and you have many different ways to remove your atoms or ions and you form such a configuration. So this is one possible way, right? So this is Ri. But I can imagine that I could do it in a different way, right? So I could do it like this. So we call this Rj. I imagine that I could consider many different randomly distributed impurities and with different configurations. So each configuration you get some randomly distributed impurities there. And you need to average over all possible configurations that you can imagine with some probability which tells you that this probability of having such a specific configurations of impurities. And we will get there next time. So in other words, what we will do is to, again, estimate this, compute this sigma 1 for this Anderson localization problem, and then try to compute the sigma, electrical conductivity. So that's the thing that we will do next time. I think that's enough for today, right? So please try to read the corresponding chapters and do the homework.